In this lesson, we are going to look at pressure altimeter errors, and we will also look at the effect of blockages and leaks. The magnitude of these errors depends to a large degree on the type of altimeter in use. We will also look at altimeter pressure settings and some simple calculations. The first error to consider is instrument error. Manufacturing imperfections and friction in the mechanical linkages cause errors throughout the operating range of the altimeter. Errors are kept as small as possible by adjustments within the instrument, and the calibration process ensures that errors are within permitted tolerances. With the simple and sensitive altimeter, however, the error increases with altitude as the sensitivity of the instrument becomes more significant at high altitude. Next is position error. This error is also sometimes known as pressure error. Ideally, the static pressure sensed by the instrument should be the true static pressure undisturbed by the presence of the aircraft. However, the presence of the aircraft will have an effect on the static pressure sensed, and position error occurs as a result of turbulent airflow and suction around the static source. In the example here, we can see the effect of a typical airflow around a combined pitot-static source. Around 90% of pressure error can be eliminated by the use of a separate static source or vent, which can be located in a place where turbulence is minimum. This is usually the side of the fuselage. However, the use of static vents is not always appropriate. In very high-speed aircraft, for example, static vents are unsuitable because of the build-up of shock waves associated with flight at high Mach numbers. These aircraft are fitted with sophisticated combined pitot-static pressure heads which keep position error within acceptable limits. Instrument error can be established by workshop measurement, and pressure error by flight trials, and a calibration card is placed beside the altimeter. This is an example for a relatively simple aircraft. The pilot then has to apply the correction by adjusting his indicated altitude. For instance, on this card, if you need to be at 4,000 feet and the correction is -50, you fly at an indicated altitude of 4,050 feet. This is an example from an aircraft with a wider operational envelope. These days, the correction would almost certainly be incorporated into a device known as an air data computer, which we will study later. The next to consider is maneuver-induced error. Again, this error is related to the source of the static pressure and is caused by short-term fluctuations in pressure at the static source. In low-speed aircraft fitted with a combined pitot-static probe, maneuver-induced error is most significant during pitch changes. In aircraft fitted with static vents, it is more significant in yaw, but even so, this is not a very large error. The fourth error to look at is time lag. With many types of altimeter, the response to a change of height is not instantaneous because of the time taken for the aneroid capsules and linkages to respond to changes in static pressure. This time lag is most noticeable when the change in altitude is prolonged and rapid, and causes the altimeter to underread in a climb and to overread in a descent. The problem is largely overcome in the servo-assisted altimeter, which does not suffer from any appreciable time lag at normal rates of climb and descent. The errors we have looked at so far arise from the design and construction of the altimeter and the pressure sensing system. When using the pressure altimeter, however, there are two further errors which need to be considered. The first of these is known as barometric error, and in the pressure altimeter it can account for the greatest error of all. Barometric error is straightforward to understand, provided we remember that the pressure altimeter is actually sensing static air pressure, which is expressed as altitude according to the pressure lapse rate of the ISA atmosphere. Let's assume that pressure at the airfield's elevation of 275 feet is 995. The pressure setting which the altimeter uses as a datum will be the one we select in the altimeter subscale by turning the setting knob. Let's now assume that the pressure at sea level is 1005 hectopascals. We can see that on the left altimeter the pressure setting of 1005 has been set, while on the right altimeter 1013 has been set. Notice that each altimeter is reading a vertical distance above its respective datum. As the aircraft climbs, we can see that the pressure setting in both altimeter subscales remains as originally set, and the indications on the altimeters will therefore be relative to the pressure datums which have been set on the altimeter subscales. If this datum pressure setting is incorrect, there will be a barometric error. Why, though, should the datum pressure that we set on the altimeter subscale ever become incorrect? The simple answer is that the local surface pressure is constantly changing. For example, we can see on this chart that the local surface pressure ranges from a high pressure of 1044 to a lowest pressure of 972. In addition, the pressures will be constantly changing throughout the day. And a change in pressure of even 1 hectopascal equates to approximately 27 feet at mean sea level in the international standard atmospheric conditions for which the pressure altimeter is calibrated. So if our altimeter subscale is not reset accordingly, there will be a barometric error. Let's see how barometric error can have a substantial effect on our actual altitude. In our illustration here, we have an aircraft with 1013 set on the pressure altimeter flying from A to B at a constant indicated altitude of 4,000 feet. We can see that when the aircraft arrives at B, the indicated altitude and the true altitude are both 4,000 feet. Now let's see the effect of barometric error if we fly at a constant indicated altitude of 4,000 feet from A to B while the atmospheric pressure is changing. The aircraft pressure altimeter is still set to a mean sea level pressure of 1013 hectopascals. But let us say that as we fly from A to B, the atmospheric pressure at mean sea level drops to 1003 hectopascals. For ease of calculation, let's assume a 1 hectopascal change in pressure equals 30 feet. When the aircraft arrives at B, the aircraft's indicated altitude still shows 4,000 feet, but look what has happened to the aircraft's true altitude. It is now only 3,700 feet. You can see what may happen, therefore, if the atmospheric pressure continues to fall and the altimeter pressure setting is not updated accordingly, especially in cloud or fog. Always remember that when flying towards an area of lower pressure than that set on the pressure altimeter, the altimeter will overread. Maintaining a constant indicated altitude will therefore result in the true altitude decreasing. The last error we will look at is temperature error. The pressure altimeter is calibrated to the International Standard Atmosphere, or ISA. So, even if there were no other errors at all, the altimeter will not indicate true altitude if the temperature lapse rate differs from ISA conditions. ISA conditions specify a temperature lapse rate of 1.98 degrees Celsius per 1,000 feet up to 36,090 feet or 11 kilometers. Unfortunately, the actual temperature conditions rarely coincide with these standard conditions, and there is therefore a temperature error to consider. Let's look diagrammatically at the effect of temperature error on the altimeter reading when flying through air which is varying from ISA conditions. Let's start by drawing lines of constant pressure and equate those pressures with altitude. If we now put an area of warm air on the right and an area of cold air on the left, we can see that the pressure levels expand in the warm air and contract in the cold air. Let's now fly an aircraft from the right to the area on the left at a constant indicated altitude. To achieve a constant indicated altitude, the pressure sensed by the altimeter must not change. In other words, we must follow a pressure level. However, in doing so, we are inadvertently following a pressure level which is actually descending, so in reality we are descending also, but the altimeter is not showing this. Our true altitude is decreasing, but our indicated altitude is constant. This is a dangerous situation. Make a note that when flying from an area of high temperature to an area of low temperature, the pressure altimeter will overread or read high. Remember, high, low, high, or, more dramatically, cold kills. When flying from an area of low temperature to an area of high temperature, the reverse applies of course, and the pressure altimeter will underread. There are three main methods of establishing temperature error so that we can work out a safe indicated altitude in order to ensure that we are at or above a required true altitude. The first is a calculation based on a formula. The second is the navigation computer. And we can also use tables, particularly for the decision height or decision altitude case. Let's look at the formula method first. We'll assume that we have the correct Q and H set. Our indicated altitude is 20,000 feet and the temperature at that altitude is -35. The first thing that we have to do is work out what the ISA temperature should be at 20,000 feet and then find the ISA deviation. Click to go on when you've done it. ISA temperature at 20,000 feet is plus 15 degrees at the surface, minus 2 degrees per 1,000 feet. That's plus 15 minus 40. You should have come up with the answer minus 25. However, our static air temperature is minus 35. This is 10 degrees colder than ISA. We can now substitute into our formula. It says that true altitude equals indicated altitude plus, open bracket, ISA deviation times 4 feet per 1,000 feet times the indicated altitude, close brackets. Our indicated altitude is 20,000 feet. And the ISA deviation is minus 10. The part in the brackets comes to minus 10 times 20 lots of 4. That's minus 10 times 80. So that's 20,000 minus 800. The true altitude is 19,200 feet. This corresponds to what you would expect. The column of air is 10 degrees colder than ISA. This means that it is denser air. Therefore, the pressure reduces more rapidly than ISA as you climb through the atmosphere because there are fewer feet to a hectopascal with denser air. So you'll pass through the required number of hectopascals to give an indication of 20,000 feet in less than 20,000 feet of true altitude. Now let's look at the navigation computer method. For this one, you don't need to work out the ISA deviation. You enter the computer with the static air temperature at your indicated altitude. We carry out the calculation using the altitude window. In the altitude window, align 20,000 feet with the static air temperature of -35. There is only one place where this can happen, so by doing this you have set up a particular relationship between the inner and the outer scales. The outer scale now shows the true altitude corresponding to the indicated altitude on the inner scale. Against 20,000 feet indicated altitude on the inner scale, read off 19,200 feet true altitude on the outer scale. In any calculation, the navigation computer will be as accurate as you need, and it is quicker and easier than the formula once you get used to it. Now get your navigation computer out and repeat this scene as often as you need to. Be sure that you are completely confident with this operation before moving on. There is also the table method. This is for use with the decision height or decision altitude. Decision height or altitude is used on an instrument approach. These are usually associated with cloud or fog, where the runway may not be visible until a late stage. If we cannot see 2 bars of lead-in lighting, we cannot continue the approach. The point at which we make that decision can be either a height or an altitude and, except for aircraft equipped with auto land, is based on the pressure altimeter. Suppose that our decision height is 400 feet. Assume a temperature of -40. At sea level, that's 55 degrees colder than ISA. It will make a difference even with a low vertical distance. Look in the table where -40 meets 400. This is a correction of 80 feet. So we must use an indicated decision height of 480 feet. We'll now summarize these errors. We have instrument error, pressure error, maneuver-induced error, and lag. The first two can be established by workshop measurement and flight trials, and a calibration card is placed beside the altimeter. The pilot then has to apply the correction by adjusting his indicated altitude. For instance, if you need to be at 3,000 feet and the correction is -80, you fly an indicated altitude of 3,080 feet. There is not much we can do about maneuver-induced error or lag except to be aware of it and not rely on the altimeter for an accurate reading when manoeuvring or in a rapid rate of climb or descent. If we correct or allow for just these 4 and set 10-13 and don't apply temperature corrections, we would be flying correctly at flight levels or pressure altitude. The next two are barometric error and temperature error. These are applicable if we wish to obtain true altitude from our altimeter. To avoid barometric error, set the right QNH and keep it up to date. And if temperature errors are significant enough to correct, this can be done by using a navigation computer, the formula, or tables. This completes the summary of errors which are inherent and are part of the normal operation of the altimeter when it is serviceable. However, there are also failures of the static system to consider, which lead to an unserviceable instrument. Let's now consider what will happen to our pressure altimeter if the static source becomes blocked. At the time of the blockage, the static pressure which was present in the system will be trapped, and any changes in static pressure which subsequently occur outside the blockage will not be sensed. In other words, the blockage will cause the altimeter to freeze at that indicated altitude. It will underread in a subsequent climb and overread in any subsequent descent. How about the effect of a leak in the static line? It depends on whether it occurs in the static line outside or inside the pressure hull. If outside the pressure compartment, or if the aircraft is unpressurized, the altimeter may continue to read correctly. However, on most aircraft there is an increased pressure error which lowers the sensed static pressure. This causes the altimeter to indicate slightly high. If the leak is within the pressurized compartment, the static line will simply sense the cabin altitude. Therefore, the altimeter will indicate cabin altitude. it will be useless until the aircraft is depressurized. Altimeter pressure problems are commonly encountered, so to conclude the lesson, let's look at a couple of typical examples. The QNH is 1025 hectopascals. An aircraft is flying at 3,500 feet altitude over an airfield where the QFE is 985. Assuming 1 hectopascal equals 30 feet, what is the height of the aircraft above the airfield? Drawing a diagram often helps, so let's do that. The aircraft is in level flight at 3,500 feet on a QNH of 1025. The airfield QFE is 985. So the difference is 40 hectopascals. This is 1,200 feet if 1 hectopascal equals 30 feet. 3,500 feet minus 1,200 feet equals 2,300 feet. Let's look at another. Assuming the indicated altitude is 10,000 feet with a local QNH set and the corrected outside air temperature is minus 25 degrees Celsius, will the true altitude be more or less than the indicated value? The way to find the answer to this question is ask ourselves what would the ISO temperature be at 10,000 feet. It would be plus 15 at sea level minus 2 degrees per 1,000 feet up to 10,000 feet. In other words, plus 15 minus 20. This is minus 5 degrees Celsius. So at minus 25 degrees Celsius, which is what the question tells us, we are flying in ISO minus 20 degrees. We are therefore in colder than standard conditions. A colder temperature means that the altimeter underreads. The true altitude will be less than the indicated altitude. This concludes the lesson. A summary of the main points of the lesson follows. The pressure altimeter suffers from instrument error, position or pressure error, maneuver-induced error, time lag, barometric error, and temperature error. Instrument error results from manufacturing imperfection, friction, and wear. The effect of instrument error in the simple and sensitive altimeter increases with altitude. Position or pressure error results from turbulent airflow and suction around the static source. The use of a static vent can reduce the effect of position or pressure error. Maneuver-induced error is caused by short-term fluctuations in pressure at the static source during attitude changes. Time lag causes the altimeter to underread in a climb and overread in a descent. Time lag is most noticeable when the change in altitude is prolonged and rapid. The servo-assisted altimeter does not suffer from appreciable time lag. Barometric error occurs as a result of incorrect setting or atmospheric pressure changes. Temperature error occurs because the altimeter is calibrated to an ISO temperature profile. In air colder than ISO conditions, the pressure altimeter will overread. In air warmer than ISO conditions, the pressure altimeter will underread. A static source blockage will cause the altimeter to continue to read the altitude at which the blockage occurs. A static source blockage will cause the pressure altimeter to underread in a climb and overread in a descent.